In 20th century, India had a great algebraist, Sriram Abhyankar. And he had a mathematical poem. The first initial lines were, polynomials and power series, may they forever rule the world. So these polynomials and power series, they are very central to modern algebra, algebraic geometry, and in fact, much of mathematics. Why I'm mentioning this is that what was behind this concept of polynomials, how did it come about? No, signal is not. So this inspiration for the algebra of polynomials, it came from decimal expansion. So decimal expansion, we tend to think of it as a part of arithmetic, but this is an algebraic concept. And in the oral form, it goes back to the Vedic Samhitas. Now, why I'm saying that this is an algebraic concept, in fact, it was the inspiration behind the algebra of polynomials. In Europe, one mathematician who is associated with polynomials and power series is Isaac Newton. Now, just see what Newton has to say. Since the operation of computing, you remember decimal system was introduced in Europe just before Newton. Since the operation of computing in numbers and with variables are closely similar, I was amazed that it has occurred to no one to fit the doctrine recently established for decimal numbers. That means the decimal system and the arithmetic. By the way, the entire modern arithmetic that we do, the rules of addition, subtraction, multiplication, division, taking square root, cube root, all these things are essentially of Indian origin, and their character is algebraic. So what Newton is saying is that to fit the doctrine recently established for decimal numbers to variables, that means the polynomials, especially since the way is open to more striking consequences. For since this doctrine in species has the same relationship to algebra that the doctrine in decimal numbers has to common arithmetic, the operations of addition, subtraction, multiplication, division, and root extraction may be easily learned from the latter. So Newton in 17th century makes a very clear acknowledgement that the polynomial arithmetic can be straight away taken from the arithmetic with the decimal system. And therefore, it is no wonder that 1,000 years before Newton, Brahmagupta had defined the algebra of polynomials, which we will see. And in the later lectures, we will also see the power series expansions in the work of Madhavacharya in 14th century. Now, I had shown the picture of Professor Abhyankar. Abhyankar, in an autobiographical article on his work, just see how he poetically puts the thing that about his, those days they had to journey by ship in the early 50s. My journey from India to the United States, he had done his graduate studies in Harvard University. Parallel the march of algebraic discoveries from India through Arabia to Europe in ancient times. So his ship went from Bombay to Arabia to Europe, and in fact, first to Italy and then to US. So embarking from the Bombay pier, my boat took the same path by which algebra had traveled from India to Europe via Arabia, where it acquired its current name. Now, so when we say that algebra was born in India, we have to be clear about what aspect of algebra we are talking about. So I make three distinctions. One is Proto Algebra, which is very ancient. So by Proto Algebra, I mean that algebra not in the form in which we are normally associate with it, the algebra that is introduced in school. So, but it is algebraic in substance, though not in external form. So let us call that Proto Algebra. And then we have the classical algebra, the algebra that we see in school. And then there is abstract algebra, which is done at a level much beyond the usual school algebra. And we see, so this I'm calling it proto-modern abstract algebra in ancient Indian mathematics. So here, abstract algebra, the language, the external form is not there, but the essence is there, the substance is there. So we will see these three parts. So Proto Algebra, as I already indicated, that there's the algebraic ideas in the decimal system and arithmetic algorithms, which are really ancient, which go back to the Vedic time, not that may not be the written notation, but at least in the oral form. The other is the Sulva Sutras, in which there have been talks earlier. So there, in the geometric constructions, you see geometric expressions of algebraic formulae like the ones which are displayed on screen. And the point is that at that time, probably algebra in the symbolic form, in the high school form, was not there. But that is the greatness of the Sulva savants, or those of the Vedic era, those Vedic savants who had invented these constructions, that they had invented mathematics, algebraic in spirit and substance, much before the genesis of formal algebra. So that doesn't make them lesser, that makes them even greater as algebraists, that even without the facilities of formal algebra, they had conceived of algebraic results in geometric form. So to give a quick example, that the construction, draw square n times the square of a square of side A, which essentially means that you have to construct root NA. So the Sulva construction is that you draw a triangle whose base is n minus 1 times A. So bisect it, and then you take your compass and draw n plus 1 times A by 2. And complete the isosceles triangle in which each of these sides is n plus 1 A by 2. And then they say that this is the required side. So what they're using here is n plus 1 A by 2 whole square minus n minus 1 A by 2 whole square is NA whole square, NA square. So in fact, this diagram is a geometric representation of the algebra formula. So this is sometimes called geometric algebra. Let me skip the next one. So now we come to algebra in the form that we know it. So what is called classical algebra, or what Professor Abhyankar would call high school algebra. So Brahmagupta in early 7th century had laid a firm foundation for algebra in the form that we know it in chapter 18 of his treatise magnum opus Brahmaguptas Siddhanta. And Fields medalist David Mumford, in a personal communication, had told me that it seems clear to me, had written to me, it seems clear to me that Brahmagupta is the key person in the creation of algebra as we know it. Now we'll just expound on Professor Mumford's statement. So the use of, let us see that what is our definition of algebra right now. So we are moving away from the Sulva geometric algebra. So use of symbols, letters of the alphabet to denote unknowns, and equations are the foundations of the science of algebra. So this is the definition which Dutta and Singh has given in their preface to History of Mathematics. And as you know, that use of symbols and equations were great steps for rapid progress of mathematics. Now let us look at it one by one. So the foundations of algebra, one is the symbols for unknowns. Brahmagupta, in the text which I mentioned, prescribes use of varna. He used the word varna, and varna has both the meanings, letters of alphabet as well as colors, as symbols for different unknowns. This is the first time there are symbols for different unknowns. And this commentator illustrates, so there was for the first variable, there was an ancient term, yavat tavat. So what they do is, they take the first letter, ya, yavat tavat, so take the first letter ya. And after that, introduce colors. So for instance, kalaka, take the first letter, ka. So ka denotes one of the variables. Similarly, nilaka, so ni. So like that, the list goes on, and I'm just giving you your X, Y, Z. So ya is the Indian symbol for X, and ka for Y, and ni for Z. I'll add one more thing for the foundations of algebra, the use of zero and negatives. And in Felix Klein, the great geometer, he had in his book on mathematics education emphasized that how extraordinarily difficult it is that when in principle, when negative numbers are introduced, here for the first time we meet the transition from concrete to formal mathematics, and it needs a high order of ability in abstraction. Now, again in Brahmagupta, we find an elaborate exposition of the algebra of positive numbers, negative numbers, and zero. That is, so first of all, zero, there is this zero as a place marker, that is much more ancient. But zero as integer in algebra, this is unique contribution from India, and this is something we see for the first time in Brahmagupta. Zero as an integer on par with positive and negative numbers. And it is defined as a minus a, zero. So that clarity, it was a profound step. And all the rules of operations with numbers, positive numbers, negative numbers, and zero, treating all on the same footing, is given. There are whole lot of rules. I'm just giving samples, like minus into plus is minus, minus into minus is plus, a into zero is zero for every number a, and so on. So here you see the dormant modern abstract algebrist in Brahmagupta, that in retrospect, he had conceptualized integers as a ring with zero as the additive identity. That is what his work amounts to saying. He didn't, of course, use the word ring. Then there is this, apart from symbols, the foundation of algebra involves formation of equations. So already in Bakshali manuscript, which many historians of mathematics date to 300 AD, around 300 AD, but some have a different point of view, some say 7th century. Let's not get into that debate. There are examples of equations there. But what we definitely know is Brahmagupta in text is 628. There he teaches about formation of equations, which is illustrated by his commentator with an example. Now, 10x minus 8 equal to x square plus 1. How Indians would represent it, how Brahmagupta would represent it is, so ya is a symbol for x and va is square, vargas. So this is, ya va is x square, ya is x, and this is the constant coefficient. So you write this 10x minus 8, so the coefficient of x square is 0, coefficient of x is 10, and the coefficient of the constant, it is 8. The dot above represents the symbol for minus. So 8 dot means minus 8. Now, instead of equality, left hand side equal to right hand side. So what they do is that there's no symbol for equality. So they, they write one below the other. So x square plus 1 is written here. So x square 1, x coefficient is 0, and 1 is here. And you will see, now you may feel uncomfortable. No, this is not what we were taught. But this is actually quite convenient for your operation, that this left-hand side and right-hand side. So when you kind of try to do clearance, there is a bit of a mental work needed. And here, this tabular arrangement of the equation makes it much more convenient, actually. So similarly, 197 minus 1644y minus z equal to 6302. So you have this ya is x, ka is y, and ni is z, and this is constant. So 197, 164 with a dot for then 1 with a dot. And similarly, the right hand side, this 6302, everything is 0, and there is 6302. So this is how equations are represented. Then next is the preparation of equations. Now, so I think there is some LaTeX problem has occurred, so that has disappeared, doesn't matter. So the equations are processed in the same way that we do now. Then equations are classified. So the point I'm trying to say is that what that classification is not important, but they have a name for equations, samikarana, and they classify, like equation in one variable, quadratic equation, equation in several unknowns. So there are various terms for that. Now, just as Brahmagupta defined, that is, gave the ring structure of integers, he actually also gave the ring structure of polynomials. See, in retrospect, Brahmagupta defined the structure of the polynomial ring in several variables. He teaches how to add, subtract, and multiply polynomials in several variables. So, like add, so he says add and subtract squares, add and subtract cubes, fourth powers, etc., of the same variable. So, like 5x squared plus 6x squared would be 11x squared, 2y cubed plus 7y cubed will be 9 cubed. But others will leave it as it is, like 5x squared plus 2x cubed, just leave it as it is, or 5x squared plus 7y squared, leave it as it is. Then the product of two unknowns is a square, product of three is a cube, etc., etc. Product of five things is fifth power, and product of different unknowns is a separate term called bhavitaka, like xy. And then operations are done on them as before. So the summary is that he is teaching the algebra of polynomials. So all this is in 628. Then quadratic equations. So that, of course, Aryabhata already had given the formula for the, that is that minus b plus minus root over b square minus 4c, but not in the form which we have seen. Their a, b, c are quantities in specific situations, like problems on arithmetic progression or problems of interest. He doesn't give it abstractly, and Brahmagupta gives the formula abstractly. That means for arbitrary ABC. And he uses the term madhya harana, elimination of the middle. Sridharacharya describes a method of completing the square, which is, of course, implicit in Brahmagupta. He doesn't elaborate, but it's implicit. And Bhaskaracharya, but Sridhar's text is lost, but Bhaskaracharya quotes the Sridharacharya method. And this is a profound idea with far-reaching significance. In fact, Professor Abhyankar talks about this resolution of singularities. The basic thing is this completing something, analogous to the completing the square. And the other point to note is that thanks to the use of negative numbers, Indians gave a unified treatment that we see now. For a long time in Europe, three different cases were studied separately. Like, I mean, these equations were treated separate. This ABC were all supposed to be positive. In India, you have uniform treatment. Then there is the solution of quadratic equations, simultaneous quadratic equations with applications in astronomy. Then Gaussian method of elimination for solving linear equations in several unknowns. Integers are, now this is very hard problem, finding integer solutions of equations. This is rarely taught in high school, even now. And these things were done by Aryabhata, that he had solved linear equations. That means found integer solutions of equations with integer coefficients, and equivalently solve the problem of simultaneous remainders, which now goes by the Chinese remainder theorem, but it is there in Aryabhata in 499. And all this work was initiated in Europe in early 17th century. This is incidentally a fundamental step in cryptography, and Indians had applied it very effectively in astronomy. Then there is the great work by Indians on the solution of equations of the form nx squared plus 1 equal to y squared, where n is a fixed integer. This was initiated by Brahmagupta, completed by Jayadev, and in Europe it was initiated 1000 years after Brahmagupta by Fermat. Now, the other thing to be noted is that in Brahmagupta, we see the recognition of algebra as a distinct discipline, because sometimes we will see that people talk about, I mean, Aryabhata doing algebra, then why Brahmagupta is thought of as the creator? Because there is there is a clear recognition of the subject as a distinct discipline. There are individual algebraic results before Brahmagupta. So for the first time, there is a separate section on algebra. And at the beginning, algebra is presented as a distinct and powerful branch of mathematics. Its core topics are listed at the beginning, that what constitutes algebra: symbols, operations with zero, negative and positives, equations. All these things are enunciated. I am not giving the full list. And he emphasizes the indispensability and power of the subject algebra. No, it's not just mathematics, focusing on algebra. And at the end of the chapter, he highlights 3 features of algebraic research. Of course, in the language of the era, gives an incentive for the delight and glory of algebra. So this intrinsic emphasizes intrinsic mathematical importance, the internal compulsion for the research. The way Ramanujan, for example, conducted his research out of the realization of the mathematical importance, and then generation of new research, and also applications. All these things are emphasized at the end of the chapter. Thus, in school, we see various series, AP, GP, all these things are there. I mean, this is even before Brahmagupta, but not in the form of symbols in terms of words. AP series, sum of squares, sum of cubes, GP, even infinite GP in Nilkantha. Then you see roots of binomial sorts are given. There's been already lectures on combinatorics in India, and so I'm not emphasizing, but there are many results, like number of permutations of n things, of which n1 of one type, n2 of another type, etc. Harder problems are also described. Bhaskaracharya takes a bold step of introducing infinity in mathematics and defining rules of interactions with usual numbers. Infinity plus x is infinity and infinity minus x is infinity. The idea of... Now we come to the climax, the proto-modern abstract algebra, what we call. Brahmagupta not only laid the foundation for classical algebra, he introduced principle of composition, which is the essence of modern abstract algebra. So composition means combination of 2 mathematical objects of a certain type to produce a third object of the same type, like composition of 2 solutions of a given equation to produce a third solution of the same equation. So let me tell what Brahmagupta's composition law is. The context is solution of the equation nx square plus 1 equal to y square, which, as I told you, that would be taken up by Farma 1000 years after Brahmagupta. Now, the point is that he looks at the more general equation, nx square plus z equal to y square, and observes that if x1, y1, z1, and x2, y2, z2 are solutions of this equation, then so is the cross product x1, y2 plus x2, y1, nx1, x2 plus y1, y2, and z1, z2. In other words, he's constructing a binary operation, and this had a name in ancient India called bhavna. Bhavna is the Indian term for composition in Indian mathematics. x1, y1, z1 composed x2, y2, z2 is x1, y2 plus x2, y1, nx1, x2 plus y1, y2, z1, z2. And this sophisticated idea of constructing suitable composition laws on abstractly defined unknown elements is a central theme in modern mathematics research, mind you, not studies, research. Now, the enormity of this innovation, think of it this way. Look at the various steps of algebra. The classical algebra is something which is done in HS, higher secondary, that formation and solution of polynomial equations using symbols for unknown. Modern algebra, so this classical algebra had simplified mathematics, and modern algebra gives you conceptual insights. There are 3 layers as the students progress. In BSc Maths, they study abstract structures like groups, rings. In MSc, they learn how to associate abstract structures to mathematical objects, like to a polynomial, with a polynomial, associate a group. And then as they go even further, and that only a few people go, I mean, those who are into algebra or number theory, they learn to construct binary composition on important set. For example, constructing an addition law on points of an elliptic curve. Brahmagupta had created number one, which we had seen. Now he bypasses this and soars to the top layer of modern algebra, that constructing binary composition. And his composition law bhavna is a principle pervading entire modern algebra and number theory. Now, I had one example to illustrate his composition law, but I suspect that I may be running out of time. So let me skip the example. You can see it in my articles. So just to give you a feeling that where Brahmagupta's law lives, there is a book, research monograph of 1990. This is a cover page. Look at its table of contents. The chapter 5 is titled Also Sprach Brahmagupta. That means Thus Spake Brahmagupta. So that is page 54. You have seen this. Page 54. What is in page 54? This is a chapter title, Also Sprach Brahmagupta. And then the Brahmagupta Sanskrit verses which give his composition law, that is quoted here. Because the foundation of this chapter 5 is lemma 5.1. And the next result, 5.2, was discovered in 1965, as late as 1965. So you see where Brahmagupta lives. So just one more slide on the inspiring legacy of Brahmagupta's bhavna. When Manjul Bhargav, our keynote speaker, received the Cole Prize, he acknowledged the ideas in his work. So he acknowledged that in his work, he has taken ideas which go back to, this is his list, Brahmagupta, Gauss, Dirichlet, Eisenstein, Dedekind, and later mathematicians. Don't you see Brahmagupta is an odd man out here? All other mathematicians are from 19th century, and Brahmagupta is tagged there. So this is where his work lives. And in a talk on Ramanujan on National Mathematical Day in 2020, he had made a remark that what Brahmagupta did around 600 just blows your mind. Indeed, there's a mathematics magazine for students, which is titled as Bhavna. It started in January 2017. You know, Manjul got Fields Medal in 2014. So this was, on the one hand, a tribute to the profound work of Brahmagupta. One thing I missed, that Brahmagupta's rule can be stated as an identity, and Euler had rediscovered it, and he called it a theorem of capital importance and a most elegant theorem. And as you can see that this is a very important identity in subsequent algebra and number theory. It is crucial ingredient in one of the theorems of Legendre. Now, this was generalized by Gauss, and he gave a composition of binary quadratic forms, which is regarded as one of Gauss's deepest discoveries. And Manjul Bhargav became famous 200 years after Gauss. He gave higher composition laws, simplifying and generalizing Gauss's theory, and that made him that has made him a legend. Now, what I was saying is that so this bhavna, this Brahmagupta's composition laws, bhavna, the concept, it connects one of the most glorious achievements of Indian mathematics of far off times with one of the most celebrated achievements of a mathematician of Indian origin in contemporary mathematics.